What is WebAssembly? WebAssembly, abbreviated Wasm, is a binary instruction format designed as a portable compilation target for high-level languages like C, C++, and Rust. It enables code to run at near-native speed by leveraging a web browser as its execution environment. Yet, its capabilities are not solely confined to web browsers. It's increasingly being used in other environments, such as Node.js and standalone virtual machines. The pseudocode represents a simple function that could be compiled into a WebAssembly module. WebAssembly modules are binary files, .wasm, which, once compiled, can be executed in a WebAssembly runtime. These binaries are more efficient to parse than traditional JavaScript and can improve the performance of applications by allowing developers to write critical performance sections in languages that are compiled to WebAssembly. History and evolution of WebAssembly. WebAssembly, often abbreviated as M, is a binary instruction format designed as a target for high-level languages like C, C++, and Rust. Its primary goal is to enable programs written in these languages to run on the web at near-native speed. Let's explore its evolution. The journey of WebAssembly began in 2015, emerging from efforts to improve the web's performance by Mozilla's ASM.js project. In 2017, the first version, WebAssembly 1.0, became an official W3C standard. Its development was a collaborative effort among major tech companies, including Mozilla, Microsoft, Google, and Apple, ensuring wide support across web browsers. WebAssembly aimed to overcome the limitations of JavaScript's performance for certain applications, providing a more efficient alternative for complex tasks such as video editing, game development, and scientific computations. Its evolution continues with enhancements to support more languages, improved debugging, and integration capabilities. Use cases of WebAssembly. Understanding the practical applications of WebAssembly, Wasm, is essential for leveraging its full potential. Wasm enables high-performance applications on the web, serving myriad use cases across various domains. Here, we'll explore some of the key scenarios where WebAssembly shines. 1. Game development. WebAssembly allows complex games to run at near-native speed, making it possible to play console-level games in a web browser without plugins. 2. Web applications. For performance-critical applications like video editing, 3D rendering, or music production, Wasm can significantly boost execution speed compared to traditional JavaScript. 3. Portable software. WebAssembly provides a platform-independent binary format. This enables software written in languages like C, C++, or Rust to run on the web with minimal changes. 4. Blockchain and cryptography. With its efficient execution, WebAssembly is ideal for cryptographic algorithms and blockchain smart contracts, ensuring security and performance. These use cases illustrate Wasm's versatility in enhancing web application performance and expanding the web's capabilities. WebAssembly and JavaScript, how they work together. WebAssembly, Wasm, and JavaScript, JS, can work together to create high-performance web applications. Wasm can be called from JS, allowing for heavy computations to be offloaded to Wasm, while JS manages the user interface and interacts with the web environment. This synergy allows developers to leverage both Wasm's speed and JS's flexibility. In this code, WebAssembly.instantiate streaming is used to load and compile a .wasm module asynchronously from the specified URL. The fetch function retrieves the module. The second parameter is an import object, which provides the Wasm module with any JavaScript functions it needs to call. Imported func is a dummy JavaScript function that the Wasm module could call. Once the module is loaded, .then is used to access the exports of the Wasm instance, allowing us to call exported func, a function exported by the Wasm module. This demonstrates how JavaScript can interact with WebAssembly, calling its functions as if they were regular JavaScript functions. Running WebAssembly in the browser. To run WebAssembly, Wasm, in a web browser, we'll use the WebAssembly JavaScript API. This example demonstrates loading and executing a simple Wasm module that adds two numbers. First, the Wasm module needs to be compiled and instantiated. Then we can call its exported functions just like regular JavaScript functions. This code asynchronously fetches a Wasm module, example.wasm, over the network, compiles it into a WebAssembly.module object, and instantiates it into a WebAssembly instance. This instance contains all exported WebAssembly functions, such as add in this case. The add function is then called with two arguments, 5 and 3, and its result is printed to the console. This process demonstrates the basic steps to load and execute Wasm code within a web environment, enabling high-performance computations to be performed alongside traditional JavaScript. Compilers and tools for WebAssembly development. WebAssembly development is supported by a wide range of compilers and tools designed to convert high-level programming languages into WebAssembly bytecode. These tools allow developers to leverage languages they're already familiar with, such as C, C++, Rust, and many more, to produce .wasm modules that can run in web browsers or on WebAssembly runtimes. One of the primary tools is the mscripten compiler, which we will focus on. This code snippet demonstrates the use of the mscripten compiler to convert a C file, example.c, into WebAssembly. The netway_s=1 flag instructs mscripten to generate WebAssembly bytecode, while nashoexample.html tells it to output an HTML file that loads the WebAssembly module. This approach allows developers to compile existing C++ codebases into WebAssembly, making them accessible in web applications without major redesigns or rewrites. Choosing a development environment. To start with WebAssembly, you need to select a development environment tailored to your project's needs. This environment can range from basic text editors to integrated development environments, IDEs, with rich features for debugging and building WebAssembly modules. While the choice of development environment largely depends on personal preference and the specific requirements of the project, it's essential to consider features such as syntax highlighting, code completion, and support for compiling and debugging WebAssembly. Popular choices include Visual Studio Code with WebAssembly extensions, or more specialized tools like Wasm Fiddle for quick experiments directly in your browser. The key is to pick an environment that enhances productivity and simplifies the development process for WebAssembly projects. Installing necessary tools and SDKs. To start developing with WebAssembly, you first need to set up your development environment. This involves installing several tools and SDKs, including Node.js, mscripten, and optionally, WebAssembly Binary Toolkit, for additional utilities. This command line first navigates to the mscripten SDK, EMSDK page, then installs the latest version of the SDK, and finally activates it. mscripten compiles C and C++ code into WebAssembly, enabling you to run C++ code on the web. After running these commands, you'll have the essential toolchain for compiling to WebAssembly. Hello World, your first WebAssembly module. In this lesson, we'll create a simple WebAssembly module that doesn't do much yet, but is your first step into the world of Wasm. The goal is to compile a basic Hello World program written in a language that can be compiled to WebAssembly. For simplicity, we'll use C. This C code defines a main function that simply returns the number 42. Although it does not print Hello World to a console, in the context of Wasm, input-output handling isn't straightforward without involving the embedding environment, like a web page or Node.js. Thus, the significance of this example lies in demonstrating the process of compiling C code to WebAssembly and executing it in a web environment. Our choice of returning 42 symbolically represents a basic form of output, keeping the example minimal. The next steps involve using tools like mscripten to compile this C code into WebAssembly, loading the resulting Wasm module into a web page, and calling the compiled function from JavaScript. Understanding the structure of a WebAssembly project. Before diving into coding, it's essential to understand the typical structure of a WebAssembly Wasm project. This knowledge will help you navigate and manage the development process efficiently. A WebAssembly project often starts with a src directory containing the source code, like main.rs for Rust projects. The cargo.toml file is a configuration file for Rust projects, specifying dependencies and project settings. After compilation, the WebAssembly binary app.wasm is usually placed in a build directory. This structure keeps the source code, build configurations, and outputs organized, simplifying the development and build process. Debugging WebAssembly code. Debugging WebAssembly Wasm requires different strategies compared to traditional web development, given its binary format and execution model. Modern tools and browsers have evolved to offer better debugging capabilities for Wasm. Here, we'll discuss using browser dev tools and external tools to debug Wasm code. Most modern browsers integrate tools for debugging Wasm, similar to JavaScript. These tools allow you to view the Wasm source, set breakpoints, and inspect variables. Additionally, source maps can be generated during the Wasm compilation process, linking the Wasm code back to its original source for an easier debugging experience. External tools like WebAssembly Binary Toolkit, WABT, also offer utilities to convert Wasm binaries into a human-readable text format, WAT, facilitating understanding and debugging of the binary code. Furthermore, custom logging and assertion functions can be injected into the Wasm code to aid in tracking down issues. Understanding the Wasm binary format. The WebAssembly Wasm binary format is designed for compactness and efficiency at both transport and execution times. It's essentially a sequence of bytes that represent a program's structure and functionality in a way that can be directly executed by a machine. To delve into this, we'll look at a simple example. This example represents a Wasm module that exports a function named add, which takes two parameters of type i32, and returns their sum also of type i32. The binary format is more compact than this textual representation, consisting of a magic number and version at the beginning, followed by sections for each part of the module, such as types, functions, and exports. Each section has a specific opcode, and the parameters and return types are represented by their own unique bytes. The getLocal instructions fetch function parameters by index, and i32.add performs the addition. This demonstrates how Wasm combines simplicity and efficiency by providing a structured yet compact binary format. Text format WAT versus binary format Wasm. WebAssembly provides two formats, the binary format .wasm for execution and the text format .wat for human readability. Both serve the same functionality but are used in different contexts. This example in text format .wat defines a WebAssembly module that includes a function for adding two integers. It's structured for human readability with explicit names and indentation. On the other hand, the binary format .wasm would compile this text into a highly optimized, machine-readable form, significantly smaller in size and faster to parse by WebAssembly runtimes. The text format is useful for debugging, learning, and writing WebAssembly by hand, while the binary format is used for actual web deployment due to its efficiency. Memory in WebAssembly. In WebAssembly, memory is a linear array of bytes that programs use for data storage. It's managed separately from the stack and can be shared between the main program and its modules. Memory must be declared and optionally initialized in a WebAssembly module. Let's explore how to define and access memory in a simple example. This sample WebAssembly module defines a memory section with one page, 64 kibytes of memory, and exports it, making it accessible outside the module. It also includes two functions, load and store. The load function reads a 32-bit integer from the start of the memory, and store writes a 32-bit integer passed as a parameter to the start of the memory. The memory operations, i32.load and i32.store, demonstrate how to read from and write to memory. The numbers preceding these operations represent the offset within the memory where the read or write operation starts. Variables and data types. In WebAssembly, variables are used to store data temporarily during your program's execution. WebAssembly is a low-level binary format, which means it has a limited set of data types it directly supports. These types are mainly numerical, integers and floating point numbers of various sizes. Let's look at how to define variables and specify their data types. In this code snippet, we declare a function that exports an operation named example. Inside the function, we define a local variable with the type i32, which stands for a 32-bit integer. We then use i32.const to push the constant value 5 onto the stack and set local to store this value in our previously defined local variable. To return the variable's value, getLocal is used to retrieve it. This demonstrates the basic usage of variables and data types in WebAssembly, focusing on an integer type and variable manipulation, functions and parameters. In WebAssembly, functions play a crucial role, allowing for code modularity and reusability. Functions can accept parameters and may return a result. WebAssembly functions are strongly typed both in terms of parameters and return values. This code defines a WebAssembly module containing a single function named add2, which takes two parameters, both of type i32, 32-bit integer, and returns a result of the same type. The function body uses local get to retrieve the values of the parameters and i32.add to add them together. The addition result is automatically returned by the function due to it being the last expression evaluated. Finally, the function is exported with the name add2, allowing it to be called from outside the WebAssembly module. Control flow constructs, if loops. In WebAssembly, control flow constructs are the fundamental building blocks that enable the execution flow of a program to change dynamically based on conditions or repeatably execute a block of code. Similar to traditional programming languages, WebAssembly provides constructs such as if statements and loops, loop and block with br-if. We'll explore how these are used in WebAssembly. The code defines a WebAssembly module that exports a function named max, determining the maximum of two integers. The if construct checks if x is less than y using i32 LTS. If x y, it returns y, then branch, else it returns x, else branch. The get local instructions access function parameters. This illustrates conditional control flow, executing different code paths based on the if condition. While not directly showing loops, it provides groundwork for understanding WebAssembly's branch instructions and conditional execution, which are essential for constructing loops and managing complex control flows. Importing and exporting functions and variables. WebAssembly modules can import and export functions, allowing them to interact with JavaScript or other WebAssembly modules. This feature enables code sharing and modularization. When a function or variable is exported, it becomes accessible outside the module. Conversely, importing allows a module to use functions and variables from the outside environment. The code snippet illustrates a WebAssembly module pseudocode that imports a function named external func from a JavaScript object JS and exports its own function internal func. The import statement defines a dependency that the module needs from the external environment, while the export statement makes internal func available for use outside this module. This setup demonstrates basic interoperability between a WebAssembly application and its host environment, allowing for seamless integration and extension of functionality. Languages that compile to WebAssembly. WebAssembly, Wasm, provides a way to run code written in multiple languages on the web at near-native speed, with a compact binary format that allows for fast parsing and execution. Several popular languages can be compiled to Wasm, enabling developers to leverage the power of the web without sacrificing their preferred tools and ecosystems. While originally designed to support languages like C and C++, the WebAssembly ecosystem has grown to include compilers for many other languages. Rust, AssemblyScript, a subset of TypeScript, C#, Go, and Python are examples of languages that now have tools to compile to WebAssembly. This diversity allows for a broad range of applications, from high-performance web applications to serverless computing and blockchain smart contracts. Compiling to Wasm involves converting the high-level source code of these languages into Wasm bytecode, which can then be executed in any web browser or Wasm runtime. This process leverages the respective language's toolchain, typically involving a compiler or a transpiler, to produce the Wasm binary. Using Emscripten to compile C++ to WebAssembly. Emscripten is an open-source compiler toolchain that compiles C or C++ into WebAssembly, enabling developers to run their code on the web at near-native speed. It's a crucial tool for bringing high-performance applications like games or physics simulations to web browsers without needing plugins. This example demonstrates a simple C program that prints "Hello WebAssembly" to the console. To compile this using Emscripten, you would use a command similar to emcc hello.c-o hello.html, where emcc is the Emscripten compiler. This command compiles the hello.c file into hello.html, which includes the WebAssembly module, an HTML file to load the module, and a JavaScript loader. The JavaScript loader initializes the WebAssembly module and provides a bridge between the WebAssembly and the browser's environment, allowing for interaction with the web platform. Compiling Rust to WebAssembly. Rust, with its performance and safety, has become a popular choice for WebAssembly Wasm development. The Wasm pack tool streamlines the process, managing the build, dependency, and publishing aspects for your Rust plus Wasm project. First, cargo install Wasm pack installs the Wasm pack tool. The Wasm pack build target web command then compiles your Rust project into WebAssembly, targeting web platforms specifically. This process generates .wasm files and JavaScript glue code, enabling integration into web applications. It optimizes for the web, ensuring the generated Wasm is lean and performant, ready for use in a browser environment. Setting up a build pipeline for WebAssembly. To streamline the development process and automate the conversion of high-level languages like C, C++ into WebAssembly, Wasm, setting up a build pipeline is essential. This typically involves configuring a series of tools for compilation, optimization, and bundling. Here, we focus on a simple example using mscripten with C code. The command uses mscripten, emcc, to compile a C source file, hello.c, into WebAssembly with an HTML wrapper, hello.html, for easy testing. The madS when calls one option tells mscripten to output Wasm code. This line forms a basic part of a build pipeline, where the compilation step transforms human-readable code into a binary format recognized by the browser. By incorporating this command into a script or automating it through a tool like Make, Gulp, or Webpack, developers can automate the build process, reducing the potential for human error and speeding up the development cycle. Optimizations and performance considerations. WebAssembly, Wasm, has been designed for efficient execution and compact representation, which makes it an excellent target for performance optimizations. These optimizations can occur at various stages of the development cycle, including during the initial compilation from source code to Wasm, and by applying transformations to the Wasm bytecode itself. Understanding these optimizations is crucial for developers aiming to achieve the best possible performance in their web applications. An important aspect of optimizing WebAssembly code is understanding the trade-offs between compilation time and runtime efficiency. Tools like mscripten and binaryeen can apply a variety of optimizations during compilation, such as dead code elimination, function inlining, and loop unrolling. These can significantly reduce the size of the Wasm module and improve execution speed. However, aggressive optimizations might increase compilation time. Additionally, developers should be aware of the WebAssembly runtime environment's capabilities, such as the efficient use of linear memory and the impact of calling between JavaScript and Wasm. Optimal use of these resources and minimizing cross-language calls can further enhance performance. Communicating between JavaScript and WebAssembly. Communicating between JavaScript and WebAssembly involves passing data back and forth, allowing both to run computations on the data. This is done through the WebAssembly JavaScript API. WebAssembly currently supports numeric types directly, and more complex data types must be encoded/decoded or shared via WebAssembly's linear memory. In this code, we start by defining an import object which contains JavaScript functions that the WebAssembly module can call. Here, imported func is a JavaScript function that can be invoked from within WebAssembly. We then load a WebAssembly module, example.wasm, using WebAssembly.instantiate streaming, passing the import object as the second argument. This operation returns a promise, which resolves with the instantiated WebAssembly module. Finally, we invoke exported func, a function exported from WebAssembly, allowing WebAssembly to call back into JavaScript by invoking imported func. The interaction exemplifies how JavaScript and WebAssembly can communicate by calling functions across the boundary. Calling JavaScript functions from WebAssembly. WebAssembly modules can interact with the JavaScript world by calling JavaScript functions. This capability allows WebAssembly to utilize browser APIs and JavaScript functions, enhancing the possibilities beyond computation-intensive tasks. To do this, the JavaScript functions must be imported into the WebAssembly module. In this simplified example, a WebAssembly module is shown importing a JavaScript function named JSFunctionName with module.cwrap, a common approach when using mscripten. COWrap creates a callable JavaScript wrapper for the WebAssembly function. The parameters define the function's name, its return type, and the type of arguments it accepts. When call JavaScript function is called from within WebAssembly, It in turn calls the imported JavaScript function JS function name with the specified argument. Calling WebAssembly functions from JavaScript. To call a WebAssembly function from JavaScript, first you need to compile and instantiate the WebAssembly module. After that, you can execute its exported functions directly from JavaScript, just like calling a regular JavaScript function. Here is a simple example demonstrating this process. In this code snippet, Wasm code is a typed array containing the binary code of the WebAssembly module. The WebAssembly.instantiate method compiles and instantiates the WebAssembly module asynchronously, returning a promise. Once the promise resolves, it yields a result object containing an instantiated WebAssembly module, which includes exported functions. Here, add is an exported function from the WebAssembly module that adds two numbers. We call this function with arguments 2 and 3, and log its return value, 5, to the console. This demonstrates how to access and use functions defined in WebAssembly from JavaScript. Passing data between JavaScript and WebAssembly. Passing data between JavaScript and WebAssembly is essential for them to work cooperatively. Basic types can be passed directly, but complex data structures need to be converted or mapped into a format that WebAssembly understands. We will explore how to pass integers and strings between JavaScript and a WebAssembly module. The example demonstrates passing an integer from WebAssembly to JavaScript. A WebAssembly module defines an exported function that takes an integer parameter and calls a JavaScript-provided log function with this parameter. In JavaScript, the import object specifies the log function used by the WebAssembly module. When the WebAssembly function is called via JavaScript with Hello World, log outputs the integer. This shows basic intercommunication, where the WebAssembly module can call JavaScript functions with primitive data types like integers. For complex data, a more nuanced approach is needed, involving memory sharing or encoding data. Handling complex data structures. Handling complex data structures between WebAssembly and JavaScript often involves encoding and decoding data in a format that both can understand. For complex types, like objects or arrays, this often means using linear memory or shared array buffer for communication. Here we'll explore a technique using linear memory to pass an array from WebAssembly to JavaScript. The code demonstrates the interoperation between JavaScript and WebAssembly for manipulating a complex data structure, specifically an array. The JavaScript part creates a WebAssembly.memory object, which is a resizable array buffer that holds the raw bytes of memory accessed by a WebAssembly instance. Then, a JavaScript function readArray is defined to read this array from WebAssembly's linear memory using an offset and length to locate and determine the size of the array. The function converts the array buffer segment into a uint8 array, allowing byte-level access, and then to a regular JavaScript array for easy manipulation. This technique ensures both WebAssembly and JavaScript can share complex data efficiently. Integrating WebAssembly with web frameworks. Integrating WebAssembly with web frameworks allows you to leverage the power of WebAssembly within your existing JavaScript applications. This can significantly boost performance for computationally intensive tasks. Here, we'll look at a simple example of integrating a WebAssembly module into a React application. The example assumes you have a compiled WebAssembly module, module.wasm, that exports a function named calculate. In this example, a React component uses the useEffect hook to load and instantiate the WebAssembly module, module.wasm, when the component mounts. The WebAssembly.instantiate streaming function is used to fetch, compile, and instantiate the module directly from the network. Once the module is loaded, the calculate function exported from the WebAssembly module is called with an argument 5, and the result is stored in a local state variable via setResult. The component then renders the result inside a div. This demonstrates a basic pattern for integrating WebAssembly with React by using hooks and asynchronous module loading. Using threads with WebAssembly. WebAssembly recently introduced experimental support for threads, enabling the use of parallel computing and making it possible to leverage multi-core processors. This feature opens doors to new performance optimizations for web applications. To use threads with WebAssembly, you typically need to use the shared array buffer for shared memory and atomic operations for synchronization. Below is a simplified example of how you might set up a WebAssembly module to use threads. In the provided code, we first fetch and instantiate a WebAssembly module that is designed to work with shared memory. We specify that the memory is shared by setting the shared flag to true in the WebAssembly memory constructor. This allows the memory to be accessible and modified by multiple WebAssembly instances or workers concurrently. After instantiation, we create several web worker threads by looping and initiating a new worker for each thread needed. These workers can then operate in parallel, reading from and writing to the shared memory established in the main thread, allowing for efficient multi-core processing within a web application. Direct memory access and shared memory. Direct memory access, DMA, in WebAssembly allows a program to directly read from or write to memory. This is particularly useful for performing operations on large datasets quickly, without the overhead of accessing the data through multiple layers of abstraction. In this example, we are using the i32.store instruction to write a 32-bit integer value into memory at an index specified by index. The local.get instruction is used to retrieve the value and index from the local variables. This demonstrates a simple use of direct memory access by directly manipulating values in the WebAssembly module's linear memory. Handling exceptions. WebAssembly's exception handling mechanism is a recent addition, offering a way to handle runtime errors in a structured manner. It's akin to try-catch blocks in higher-level languages, providing a way to write more robust and error-resilient WebAssembly modules. Security considerations and sandboxing. WebAssembly provides a secure execution environment by default, running code inside a sandbox. This ensures that WebAssembly modules cannot directly access the host system's memory or other resources without explicit permission. Let's explore how this security model benefits WebAssembly applications. WebAssembly executes inside a sandbox environment, providing a layer of isolation from the host machine. This is crucial for security, as it prevents Wasm modules from executing harmful operations, such as accessing or modifying system files. Despite being limited to sandboxed operations, WebAssembly can still perform tasks efficiently, with tightly controlled communication to the outside world through well-defined interfaces. This ensures that applications remain secure, while still being able to interact with the broader system as necessary, under strict controls. Interoperability with other web APIs. Interoperability between WebAssembly and other web APIs is crucial for building complex applications. WebAssembly Wasm modules can interact with JavaScript to access web platform APIs like the DOM, Fetch, and WebGL. This example illustrates calling a JavaScript function from Wasm to fetch data from an API. This code demonstrates loading a WebAssembly module using WebAssembly.instantiate streaming, which fetches and instantiates a Wasm module directly from a server. It then extracts the fetch data function from the module's exports. This function is defined in Wasm, but is designed to interface with JavaScript to make web API calls, for instance, to fetch data from a remote server. The code shows interoperability, where Wasm and JavaScript collaborate to utilize web APIs, combining Wasm's performance with JavaScript's extensive API access. Optimizing WebAssembly code for size and speed. Optimizing WebAssembly Wasm code is crucial for performance and efficiency, particularly for web applications. This involves reducing code size for quicker downloads and enhancing execution speed. We'll focus on strategies including using efficient data structures, applying compiler optimization flags, and minimizing the use of imports and exports. This command leverages the Wasm opt tool, part of the binarian suite, to optimize a WebAssembly module named myModule.wasm. The -oz option instructs Wasm opt to perform optimizations focused on reducing code size drastically. While this example is simple, in practice, optimizing involves iterative adjustments and profiling to balance between execution speed and code size effectively. It's pivotal to test the optimized Wasm module to ensure that functionality remains as expected, as aggressive optimization can sometimes alter program behavior. Project structure and best practices. Organizing a WebAssembly project effectively is crucial for maintainability and scalability. Below is an example structure and some best practices for setting up a WebAssembly project. The SOS directory contains the Rust source files, main.rs for the entry point, and lib.rs for the Rust library that gets compiled to WebAssembly. The build directory is where the compiled WebAssembly and any generated files would reside. Tests directory is for unit tests to ensure code reliability. Cargo.toml is the Rust package manager's configuration file detailing dependencies and project information, while readme.md provides an overview and instructions for the project. Organizing the project this way promotes separation of concerns, cleaner code, and easier management. Integrating WebAssembly in existing applications. Integrating WebAssembly, Wasm, into existing applications allows for performance optimizations by running critical parts of the application's code in a faster, more secure sandbox environment. This is particularly useful in web applications for computationally intensive tasks like image processing or physics simulations. The process involves compiling part of your application or algorithm to Wasm and then calling this Wasm module from your existing JavaScript (JS) codebase. In the provided code, WebAssembly.instantiate streaming is used to asynchronously fetch and compile the WebAssembly module named module.wasm. The fetch API is passed the URL of the Wasm module as an argument. Once the module is fetched, it is compiled and instantiated. The instantiate streaming method streamlines the fetch and compile steps into a single operation, which can lead to performance improvements. This process also ensures that the compilation is done in the web worker thread, preventing the main thread from becoming blocked. After compilation, the module's instance is passed to a function go.run, which is a placeholder for the procedure to execute our WebAssembly module's exported functions. This approach demonstrates basic integration, where a predefined Wasm module is incorporated into an existing JavaScript application to enhance its performance or functionality. Building a full application with WebAssembly and JavaScript. Integrating WebAssembly, Wasm, with JavaScript, JS can significantly enhance the performance and capabilities of web applications. Wasm allows you to run code written in languages like C, C++, and Rust on the web at near-native speed, which can be particularly useful for resource-intensive operations. In this scenario, we'll see how a simple calculation written in Rust can be compiled to Wasm and then called from a JavaScript-based web application. The Rust code defines a simple function add that takes two integers and returns their sum. This function is annotated with #wasm bindgen, indicating that it should be exposed to JavaScript when compiled to WebAssembly. In the JavaScript code, the add function from the generated.wasm file is imported and used just like any other JavaScript function. The import statement requires WebAssembly module support or a bundler capable of handling .wasm files like Webpack. This setup exemplifies how WebAssembly modules can be seamlessly integrated with JavaScript, allowing web applications to leverage the performance of Rust or other low-level languages without sacrificing the convenience and ecosystem of JavaScript. Testing and debugging strategies. In this section, we will explore strategies for testing and debugging WebAssembly, Wasm applications efficiently. Testing is crucial for ensuring the reliability and performance of applications, while debugging helps in identifying and fixing errors. Our focus will be on leveraging existing tools and methodologies effectively. This code snippet demonstrates how you can use console logs and browser developer tools, such as Chrome DevTools, to debug WebAssembly applications running in a web environment. Console.log allows you to print messages that can be viewed in the browser's console, providing insights into the application's runtime behavior. Setting breakpoints, as the comment suggests, enables you to pause the execution of your program at a specific line, inspect variables, and step through your code, which is invaluable for diagnosing issues. These techniques form part of a broader strategy to test and debug WebAssembly applications, complementing more sophisticated methods like unit testing and using the WebAssembly-specific debugging tools. Deployment and distribution. Deploying and distributing a WebAssembly application involves packaging the compiled .wasm module and the necessary JavaScript glue code for bootstrapping. This demonstration shows a basic example using a bundler like Webpack for simplicity. This Webpack configuration file shows how to set up a project to bundle a WebAssembly.wasm file along with its JavaScript calls. The entry defines the starting point, while output configures where the bundled files will be placed. The module.rules section includes a rule for handling .wasm files, using Wasm loader to properly load these modules. This setup allows for efficient deployment and distribution by combining the WebAssembly and JavaScript parts into a single optimized file. Performance monitoring and tuning. In the context of WebAssembly, performance monitoring and tuning involve analyzing the runtime behavior of your applications to identify bottlenecks and optimize execution speed. This ensures your WebAssembly modules perform optimally in various environments. We'll explore how to use browser developer tools for this purpose. The given code snip is a basic example of using the Web Performance API available in modern browsers to track how long a particular operation takes. The performance.now method returns a high-resolution timestamp measured in milliseconds, which can be used to monitor the performance of your WebAssembly code. By placing calls to performance.now around sections of your WebAssembly invoked functions or operations, you can measure how long they take to execute, helping identify slow spots that need optimization. This approach is a simple yet effective way to start with performance tuning in the context of web applications. Upcoming features and proposals. One of the anticipated features in WebAssembly's evolution is the introduction of garbage collection, GC. This feature aims to facilitate complex data structures directly in WebAssembly, enhancing interaction between WebAssembly and host environments like JavaScript. The code snippet presents a conceptual example of how garbage collection might be defined in WebAssembly's textual format. It declares a custom-type $list node as a structure, struct, comprising two fields, an i32 integer and a reference to another list node. This demonstrates how WebAssembly could natively support linked list data structures with automatic memory management, eliminating the need for manual allocation and deallocation once fully implemented. WebAssembly outside the browser, Node.js and Wasm. Traditionally, WebAssembly was designed to run in web browsers, providing a way for high-performance code to execute alongside JavaScript. However, its potential outside the browser, particularly in server-side environments like Node.js, has been increasingly recognized. This enables applications to utilize WebAssembly modules for computationally intensive tasks, leveraging their speed and efficiency. In this code snippet, Node.js is being used to load a WebAssembly module from the file system. The fs module is used to read the WebAssembly binary mymodule.wasm into a buffer. Then, the WebAssembly.compile method is called with this buffer, compiling the binary into a WebAssembly module that can be instantiated and used within the Node.js application. This illustrates how WebAssembly can be integrated into server-side applications to take advantage of its performance benefits outside the browser environment. Interacting with the host system via WASI. WebAssembly System Interface WASI provides a standardized way for WebAssembly modules to interact with the operating system. This allows WebAssembly applications to perform I/O operations like reading from the file system or the network in a secure and portable manner. Here's a basic example of how a WebAssembly module can use WASI to read a file. This code snippet is written in WebAssembly text format, WAT, showing a module that imports a fdread function from WASI snapshot Court Preview 1. This function is used to read data from a file descriptor. The module can use this function to perform file read operations by passing the appropriate arguments, which include the file descriptor, a pointer to a buffer for the data, the buffer length, and an address to store the number of bytes read. WASI Snapshot Preview 1 is a version of WASI that offers various APIs for file operations, environment variables access, and more. This example demonstrates how WASI facilitates interaction with the host system's resources in a secure manner. Portability and cross-platform development. One of the core value propositions of WebAssembly is its portability and ability to run on multiple platforms without modification. This is made possible through its binary instruction format, which is designed to be both compact and efficient for execution within various environments. WebAssembly modules are compiled from languages like C, C++, or Rust into a binary format, .wasm. This binary is then executed by a WebAssembly runtime, which can be embedded in web browsers, servers, or even IoT devices. Portability arises because the same .wasm file can run on any platform that has a WebAssembly runtime without needing to be recompiled or adjusted for the specific architecture. This eliminates the common challenges of cross-platform development, such as dealing with different system APIs, toolchains, or performance quirks across platforms. It essentially enables write once, run anywhere capabilities for complex applications. Community resources and how to contribute. The WebAssembly ecosystem is vibrant and rapidly evolving, with numerous projects spanning various domains, such as gaming, blockchain, and serverless computing. Engaging with community resources and contributing can enhance the ecosystem and your understanding of WebAssembly. Below is an example of how you might contribute to an open-source WebAssembly project using Git and GitHub. Here, you first clone the repository of an existing WebAssembly project. After moving into the project's directory, you create a new branch for your feature. Once you've implemented your awesome feature, you commit your changes and push the branch to the origin remote. Finally, using GitHub's interface, you submit a pull request PR with your contribution. This process allows project maintainers to review your contribution and possibly merge it into the main codebase, facilitating collaborative improvement and innovation within the WebAssembly community.